So now that we have an input stage and an output stage, the question that we first can answer is if there is an overlap in requirements. So that's what we have studied. If there's an overlap in requirements for noise and for ranges, let's say for the ranges we determined for the length and the width and the multiplication factor and the current, if there's an overlap for the input stage and the output stage, then maybe we can make a single stage amplifier. So the whole controller of our negative feedback amplifier can be a single stage. I skipped this here, but it is still a thing you can investigate, but we found out that the loop gain was very low and distortion was not low enough. So that's why we went for immediately the two-stage solution. But it is not necessary if you have an overlap between the requirements for the device of the input stage and the devices of the output stage, then maybe you can make a single stage design. So what we are going to do, we are going to design the midband accuracy and the amplifier bandwidth in this step. And the thing that we need is the midband loop gain and the loop gain pulse product. That's what we are, that's the design aspect that we are going to focus on to fix, to set this to a value that we want. And we can use this slide cap from the previous studies. We have the values for the operating points, and that we just enter in the models of slide cap, and we find the GM and the capacitors, etc. And we can completely finish our design up to frequency compensation in slide cap. And later on, only for weak nonlinearity later, we need to go to biasing. So really we are building it up step by step. There's no interaction with other things. We have designed the two stages. If we keep the operating currents as defined, we just put these two stages together, and then we can evaluate the loop gain pulse product. If we have two inverting stages and we need to have a feedback, and that would make a loop with a non-inverting loop transfer, then we would have positive feedback, and we need to do something about it. One way of doing something about it that we found is use a balanced stage for one of the two stages or for both stages, but that does not necessarily change our conclusions, because we know if we go, for example, from a single CS stage to an anti-series stage, that we can have exactly the same performance if the transistor is each transistor is 2 times wider, and the current in each transistor is 2 times more as that of the single CS stage. Then we have the same noise performance, and we have the same A, B, C, and D, and only the nonlinearity for the even components has changed. So it means that we can take really the decisions independent from each other. Later on, we can define, even though we have analyzed, for example, for the noise, a single CS stage, we don't need to do this work again if we go to a differential pair, because we know the conclusions, we know how we migrate, let's say, basically from a CS stage to a anti-series CS stage. So what we have as a degree of freedom, if we don't have the bandwidth with our two stages, so if we have it, then we have no problem, but if we have it, then we have another degree of freedom, which is independent of what we already did, because we selected the CS stage for input stage and for output stage. It means that they have the best nuller approximation for those stages, and the distortion will mainly be determined in the output stage, and the noise will mainly be determined by the input stage. So the number of stages then just increases the loop gain pulse product. If we add another stage, we can just increase the loop gain pulse product. And that is what we want. And in this way, we can design bandwidth independent from the other aspects. So that's why you don't see any blue blocks in the roof. So we are going to find out the number of stages, and the first thing we do, of course, is as I said before, you could start with one stage, evaluate the loop gain pulse product, see if it's okay, then evaluate, then go to the next step, and then you see the non-linearity will not be good enough and you need two stages. Now I skipped one, so I immediately went for investigation of the two stages. So for the active antenna, we are going to use the asymptotic gain feedback model to verify the loop gain and the loop gain pulse product of this two-stage solution. That's what we will do in the following 5 minutes. Here was the idea. We could replace, I said before, if we have two non-inverting stages, and we have in this case, then we can use a differential pair, for example, as input stage here, to take the other output terminal and have a inverting loop transfer instead of non-inverting. That is probably the best solution, and we left it up to you. So you have the honor to do the best solution. Let us work with some inferior one, and just for the demonstration of the process. And we are not going to sell this amplifiers, I promise you, but it's just for the educational purpose that we do this one with a inverting current amplifier between the first and the second stage, knowing that this can easily be implemented later on with a simple current mirror. But you have the assignment to make this amplifier with a differential pair, and probably you will have a much better performance than we in this way. So let's go to the small signal equivalent diagram. If the current mirror, the non-inverting current amplifier, it's drawn on concept level here, it shorts the first stage and it drives the second stage with a current. So let's say basically I can replace the whole thing by just swapping the sign of GM, keeping a simple model. So now I have inversion in the loop, you see. So which means that this is a loop equivalent diagram, the lower figure that is valid for this one, but also for your differential pair. Only GM has another value and CISS has another value maybe, but if you make your devices twice as large and per device twice the current, you have exactly the same model. So you may expect the same result as we have. Only later on we are going to implement this non-inverting current amplifier, this inverting current amplifier as a current mirror, and then we add another pole, and you don't do that. You have already here your complete model. That's why probably your solution will be easier and better in the performance. So for this circuit, we choose GM1 as reference. We calculate the loop gain. Well, that you can easily do. It's just a capacitive divider here, and you have an integrator here, and you have RC time constant here. So that's all in this expression. And from this, you can calculate the loop gain in the pulse product. And you find we have two poles. There's one S here, and there's another S there. So you have two poles, and if both poles can be dominant, well, one is in the origin, so it's always dominant. And if the other one is not too far away, it is also dominant, and we can have a second order LP product. We will check out later if the pole will be dominant. That's by doing the second, we need the numbers. So the circuit element values we get from SlideCap. So this is what we get from SlideCap. So for the GM of the two stages, for the input capacitance based on the noise design, and the output capacitance, the input capacitance of the output transistor based on the drive capability. If you put that all in the equations, and the nice thing you see, CF is not affecting the loop gain. You see, CF, it drops. The loop gain pulse product, there's no CF in. And that is why I like to make it first completely in a symbolic expression, and then later on fill in the values, because this gives us a lot of information. Basically two integrators, GM and GM1 and CSISS1 plus CS, so this one, and GM2 and CISS2. There's 2 integrator stages, cascaded, that's all. And then we have the product of the integrator gains as loop gain pulse product. So the achievable bandwidth, if both poles are dominant, and for the moment we assume it is 1.5 gigahertz. We check both poles in the next step, but we already did it. The sum of the poles was 450 megahertz, so the second pole was about 450 megahertz, which means it is definitely dominant. 1.5 gigahertz is much more than we need. We need only 30 megahertz, so here we can conclude